Today I am thrilled to introduce Dr. Nori Nakata. He is a staff scientist at the Energy Geoscience Division at the Lawrence Berkeley National Laboratory and a principal researcher scientist at MIT. He received his Bachelor's of Engineering and Master of Engineering degrees from Kyoto University and his PhD from the Colorado School of Mines. So Nori's research interests include, but are not limited to, crustal global seismology, exploration geophysics, volcanism, civil engineering, wave phenomena, earthquakes, and microseismicity. So today he will be giving a presentation titled Unraveling Shallow Ice Structure with Active and Passive Seismic Surveys at West Antarctica. So if you'd like to share your screen, Nori, and we can get started.
Okay, yeah, thank you very much, Eleanor, for great introduction, and thanks, Marco, for the invitation. Let me share my screen. Hope everyone can see it now. Okay, great. So today I'd like to focus on one topic. Recently, I'm very interested in about shallow ice structure at Antarctica, and this is really international programs. On US side, NSF is one of the main funding source, and also there are European funding as well. And this team decided to bring seismic surveys, like both passive and active, means there are active sources and also receivers, also some GPR and other geophysical tools to Antarctica to understand the ice dynamics and also the ice shelf, stability of the ice shelf and so on and so forth. And today's talk is related to the waste divide. If you're familiar with, this is close to the US camp, and we did some test surveys in 2019, and we start having some ice shelf images. So I'd like to focus on that. And the entire project is not focused on this part. Like we are more interested in the Thwaites ice shelf, the West Antarctica, and how stable it is. So this is sort of a test data set, but still very interesting result we obtained. So that is something I'd like to share. So this is the location of the survey in 2019, and we put some very weird shape seismic arrays. So there are seismic sources along this line, and also put many seismometers on 2D line and also circle shape. And then so on this line, we have about 80 sensors and 20 sensors on this circle. And the main purpose of this survey is for testing the different types of active sources. We use explosion, polter shot, and also some sort of impulsive source as well, and check what's the best source for us. That part is I will not really touch today. I'm more talking about the ice shelf image itself, and how dynamic it is and what we can find from that kind of data. So I'm more focusing on this line today. This line records ambient noise and also active seismic data. So I will use this data. There are total 103 component sensors. Probably you're very familiar with this. Is the size of the node, like single node, and inside of that there are 3 component sensors: battery, memory card, GPS. Everything we need is in this package, and we deployed we vary inside of the ice and record for 7 days total as minimum. Some stations recorded a bit longer than that. And as you can imagine, like the field deployment is a little bit unique at Antarctica. So bringing them is already very hard. That we use like this kind of like settings and the snowmobile to deploy them. Active sources, this is one of the examples, like portal shots we use. Like portal shot is there's a like explosion at like above ground, and there's a like metal rod there, and then once explosion there, like seismic energy propagate along this bar, and then hit to the ground, and we get the sort of like P waves energy penetrating inside of the ground. This is very like old-fashioned shot. Like I think like there's a patent in like 60s or even 50s, and then we understand like this is pretty efficient for the Antarctic survey. So because it's fast and also uh, the quality is good. Detonation code is a little bit problem to deployment, like it takes time. Shallow drilling shot has very good quality, but like drilling and exclusive source inside of the ice is always like question of the environment. So like portal shot is so far the winner for us to do the survey. And then, okay, let's start going to the observed data we have. So this is a typical shot gather. So source is at this star location and receivers along the line. So there are about 80 stations, and that is along this line. And source is like 0 second around here. So I think like you see very interesting features already that we see P waves and sort of S waves here and surface waves here. So change and then like there's some reflectors, PP reflectors, and then also PS reflections and like converted waves, and this is the PS reflections from the at the bottom of the ice. So PP is basically like propagating starting from the source to the surface, and then bottom of the ice, top of the ground, and then reflect back. And then this is the air wave. So air wave propagating at the surface, I mean above surface, and this is propagate around like 300 meters per second. So, and then because of the source type, transverse component doesn't record very coherent waves. If you are interested in, like we are about submitting a paper for the different types of sources sometime soon, and we submitted another paper about the image of the active shot. And that is part of today's main talk. And I will come back to the active seismic part later this talk. The first talk about the ambient noise part. So ambient noise part is from the continuous recording of this survey. So survey is 30-meter sampling of the geophones. So receiver spacing is 30 meters and 7 days of recordings. And because like our maximum offset is 2.2 kilometers, and frequencies we can use is like between like 2 to 20 hertz. I will show you in a minute. The penetration depth of the surface waves is about like 300 to 400 meters. And then this is sort of the pre-processing we did before ambient noise correlations, and like sort of like detrain the mean, that's very conventional instrument response removal, and then apply the bandpass filter and to enhance a bit of signal to noise ratio. And then this is a typical ambient noise correlation gathers. So we also call like this is virtual shot gathers. And then reference receiver is at the at trace 1. And then wave propagation there. So there are some similarities between active short and passive ambient noise correlation gathers. This is the main part is the surface wave. So this is the radio waves we have. And then you can see some here that is P-body waves. And then for ZR component is pretty similar to ZZ because this is also the PSB wave types. And the TT component slightly different, like lab waves or SH waves, and then lab waves are slightly faster than the radio waves here, and less coherent because possibly because like radio waves are more excited strongly by nature than lab waves. So that's what something we can see here. Here, like we see a bit of the bend of the direct waves. So you see, slightly different phase of the wave at this location. And then when we check the particle motion, we also see that station is something unique. And so this is the DG and DR particle motion at different offset. So using same station and taking a different offset. And then this is something I calculated. And except the trace 38, the particle motion are quite similar each other. And only the trace 38 has a slightly different particle motion. That is interesting. And so far, like we didn't find any surface changes at this station, but we eventually find some structure changes after doing some ambient noise correlation. So this is a very interesting signals at the end. A bit more of the particle motion analysis. So this is one trace I take from the ambient noise. So this is one station here, and then compare the two different components again. So this is RR and RZ component, and then we see very fast wave, intermediate wave, and this is like strongest wave I show you. This is radio waves, and the radio wave particle motion is something like this. And then the P wave part is more like a linear trend we have. So no phase differences between two components, and then this angle can provide you the incident angle of the wave. And the second wave, we are first not sure the wave types, like either S waves or the higher mode surface waves. And then eventually we understand that this is probably the surface waves because first of the higher mode because of the particle motion. So the particle motion can tell us more like this could be the surface waves too. Going to the imaging part. So we did we calculate the slowness frequency spectra, and this is like very simple like dispersion curve analysis, and the radio wave component, lab wave component, radio wave component. This is DG component. I also use GR and RR component, and then we see very strong strong fundamental mode and some higher mode are there. Probably, like other mode, we can see possibly S body waves, but this is we conclude more for the higher mode surface waves. Lab waves are like more let's say noisier, and also like many other waves are observed because like fundamental mode is not as strong as radio waves, so we can see like multiple different modes. And the leaky mode, I will explain more for the active source part. And then instead of doing the conventional like 1D seismic velocity inversion using the dispersion curve of these surface waves, we do the sort of full waveform inversion to do the velocity inversion velocity estimate, which is written here. So we use like a local cross correlation between the observation and synthetic at the frequency velocity domain. So this is really this domain. And with phase. So this is amplitude, and we also use phase as well. And then some weighting function we put at the like object function, try to minimize it. And then I will skip all the detail of the inversion part, but this is what we observed from the data. So SV waves and SH waves are independently inverted using the TT component and other components. And then the last figure is showing the SHFB ratio. So this provides us the anisotropy, like especially like radial anisotropy strength. So as we kind of expected, the SP and SH velocities are quite laterally homogeneous. And because like in 2 kilometer areas, ice doesn't really have the much heterogeneities because there's a snowfall and then compacting, and like more compaction, and then like snow becomes to ice eventually. So that doesn't really have the provides a much heterogeneities. And then the interesting thing is we have quite dramatic velocity changes, like velocity increase in the top 50 meters. This is the effect of the compaction, like the near surface is very sort of soft ice or soft snow. And then the within 50 meters, the velocity is probably doubled by this scale, and then that is the effect of the compaction. I mentioned like the station 38 at the beginning, and we find that the anisotropy ratio is changing at this station. So this station, like we didn't find any surface signatures, but by imaging, we understand that there's a like anisotropy signature or VP, like SHSV velocity ratio changes quite dramatically. So that is really interesting. We are trying to compare this with the GPL data right now. We don't really have the physical reasons yet why like we have this kind of changes, but at least like there's a like strong lateral heterogeneity of the anisotropy of the ice. This is interesting. More like more comparison of the velocity profile, BSB and BSH. So you can see some like anisotropy, like the ratio between BSH and BSB changes over the depth. So you can see that. And this is anisotropy part. The quality of the inversion. So this is a comparison of the spectra the observation and initial velocity model. Initial velocity model is we take from some literature, and then like this is inverted velocity model. So as you see that the spectra seems much similar to the observation after inversion. That is something we expected. And this is the waveform comparison. So this is including the phase part as well. And so as you can see, probably like you see more similar with inverted velocity waveforms and observations, but this is more easy to confirm after the cross correlation between this and that, or this and that. So this is a cross correlation between initial round observation. This is the cross correlation between final round observations, and you see like phase is more close to time lag equal 0, which means the phase between final round observation, like inverted round observation, is much similar than the initial. Same things for SH. The waveforms I'm sorry, the spectral becomes much similar. That is great. Although we understand that there are probably some overfitting problems because like inverted spectral has quite a bit of the details shown in observations, and that is maybe above the resolution of the waveform. So that is a bit of caution, but in general, like we get a very good similarities, and the shape of the high power part is really the same shape. And then again, like this is a cross correlations, and then after inversion, the phase is almost matching pretty well to the observation. So that's good. I will come back to this wave later. So this is observed inverted velocity model, and we are further interested in the very near surface part, especially the top 100 or 50 meters, like low velocity zones. The reason like why we are interested in the low velocity zone is because the surface of the ice is probably most dynamic part of the ice structure, and also the water content inside of the fan. So we call like this like near surface part like snow fluffy layer is a fan layer, and the water content inside the fan layer is really controlling factor of the ice dynamics. Like after we have some melt, and also like the movement of the fluid. Once we reach to the critical condition, the fluid start migrating or melting the ice in the vertical direction, and that creates like vertical fractures, and then that vertical fracture provides a weak plane, and that breaks the ice shelf, and that is one of the problem right now for the climate change. So understanding the fan layer and the property of the fan is really important for us. And then like we apply the H over V spectral analysis. If you are familiar with, this provides higher sensitivity at the near surface. So what I show here is phase velocity of the RR component. This is same as what I used in the previous study. And then H over V ratio calculated at each locations. Because like receiver spacing is 30 meters, and we are interested in very high frequencies, for this analysis, like H over V analysis, I didn't really use like 2D inversion. Instead of that, I applied the conventional 1D inversion to estimate the velocity model at each locations. And then this is a sensitivity kernel, so it's a little bit hard to see, but you see, so this is a phase velocity, normal surface wave sensitivity kernel, and the HOV, you can kind of see like concentrating around here. So high sensitivity in top 20 meters, and even at very shallow part, like few meters, we have also the very high sensitivity. So that is the reason why like we want to use HOP spectrum. And then this is jumping to the result. And because like we estimate the profile at each location, the smoothness, like lateral smoothness, is not very well, but we can still see some trend, and at least like we see very near very low velocity zone at the near surface, and this is probably surprising that the velocity is like 200 meter per second, or sometimes even lower than that. And that makes sense because if you imagine like snow containing a lot of air, and then shear wave velocity becomes nearly zero because and the shear wave velocity of the ice, shear wave velocity of the air is 0 meter per second. So they cannot propagate S wave velocity. So that's why the near surface part S wave velocity is quite low. And then as we found with 2D inversion, the velocity increased quite dramatically in the very shallow part. Compared to the 2D inversion, I just show you like I just use the same color scale. You can see like how detailed we can observe from the 1D inversion. So 1D inversion is probably like more conventional, but if we are really interested in the near surface properties, this inversion is still quite useful to apply. And then below 100 meters, the H1B doesn't really have the sensitivities, and the 2D inversion might be the better idea to use it. Okay, let's get back to a bit about this part. So we see a little bit of like reflections in SH wave, and when we image them, it shows the image around 1.7 kilometer depth from the surface of the ice. It's very interesting because the depth of the ice, thickness of the ice around this area is 3 kilometer depth. So this is really the inside of the ice layer, and it's still like under the debate, but probably the possible interpretation of that reflector is due to the crystal size. So there's the change in the crystal size around 1.7 kilometers at the Antarctica, like the waste divide area, and that crystal size changes can provide the impedance contrast, S-wave impedance contrast, especially very strongly for S and not so much for P for the crystal size. And that's why like we kind of think like this could be related to the crystal size changes. And we are trying to compare more with the ice core data right now. Okay, before finishing, let's touch to the active seismic part, and then conclude my talk. So this is the same short gather as I show you in the beginning, and as I said, like these are very interesting features, especially like direct after direct P, you have a lot of very repeating signals, and the same for S, and probably same for surface waves. Surface waves, like we kind of know why, like this is different depth penetrations, and the high frequency is slower. That's the same game as normal surface waves. And then we see the very clear reflected waves, reflected PP waves. And then when we apply the imaging techniques of these PP waves, we get something like this. So because like the array is kind of sparse, we don't very much have a smooth reflector image, but we can still see, some sort of deflections. So this part above 3.2 kilometer is ice, and below 3.2 kilometer is the ground. And we see a lot of we see very strong reflections from the bottom of the ice bed. What's interesting is we see also a bit of deflections inside of the ice, and this is because of the mixture of the ice and soil. So this layer, like around here, like 500 meters above the ground, the ice is not very much pure ice. It's more like the mixture of the soil and the ice, and then that's probably why like we have the deflections inside of the glacier. That is very interesting, and we are trying to understand more about what's the physical meaning of the thickness of the this ice part and ice soil interactions. And then these reverberations, looks like reverberations, can provide us more information of the P waves indeed. We confirm by modeling that this is a leaky mode, and the leaky mode is sort of the surface waves, but the guided waves of the P waves is a leaky mode here. So typically, like what we are seeing for the surface waves is sort of the guided waves of the S waves is near surface is surface waves. Leaky mode is guided waves of the P waves in the near surface. So the travel time is very close to P waves, and then we have the dispersion curve. So this is a dispersion curve. So leaky mode is frequency dependent. The phase velocity is much faster than the typical surface waves. This is like more close to the P wave velocities. And then there are also the higher mode. We can definitely use these waves for the inversion, and then we invert the near surface P waves as well. And this is a velocity models we obtained. So usually, like when we use only surface waves, it's very hard to access P waves, but the P wave velocities. But if you see the leaky mode, that is a chance. Like you can get a very high resolution BPPS ratio, for example, at the near surface. Leaky mode is strong in very special condition, like a BPPS ratio needs to be greater than some values. I don't remember exact value, but it probably needs to be larger than 2 or 2.2 or something like that. But like if you see that could be really an interesting way. And after the inversion, we can also compare the observation and the predicted waveforms, and you see like all of the perfect match in the first like 5 wavelet between observation, which is black, and the prediction, which is in red. We see a bit of not much in the later quarter part. Maybe like this is related to some sort of structural information. We need a bit of like heterogeneity to explain this part, which we couldn't really invert yet. Okay, this is a final slide. So we bring the seismic surveys at the West Antarctica. This is already a big challenge for us. And then we use the observed data to characterize the near surface ice structure. Near surface ice structure has not really been studied well yet. And these seismic data can be very useful for us to study these structures. And then SH reflection we found, englacial reflections also is interesting, and then also like leaky mode can explain the near surface P waves. So all about my talk. Thank you.